Bismillah ar-Rahman ar-Rahim. Last lecture we talked about NAND and NOR gates, okay, and their universality and how to convert circuits, whether two-level or multi-level, okay, to NAND or NOR implementation. This lecture we are going to talk in depth about XOR and XNOR gates, okay. These gates are composite gates, okay? They are not primitive like AND and OR and NAND and NOR. These gates, the NAND and NORs, and are considered primitive gates, okay? However, XOR and XNOR gates are composite gates, because you can see here from the truth table of the XOR gate that we have seen before, okay? You can see that A XOR B evaluates to the sum of minterm number 1 and minterm number 2. So it is XOR A XOR B is 1 whenever A does not equal to B. You can see that, all right? When A equals B, the XOR is 0, all right? So whenever A does not equal to B, we have minterm number 1 and minterm number 2, and these two minterms are listed here algebraically. Okay, so A XOR B algebraically equals to A complement B ORed with A B complement, and you can see that this is irreducible. It's the simplest form. Okay, you cannot simplify it any further. So the XOR gate is composed of inverters, two AND gates, two inverters, two AND gates, and one OR gate. So it is a composite gate. Okay, similarly for the XNOR gate, it is composed of the same with an additional inverter, or you can also implement it using sum of minterms as well, because the minterms are number 0 and number 3. Okay, so my A XNORed with B, so we have A XOR B complement, is equal to A complement B complement, ORed with AB, right? ORed with AB. These are the two minterms here. And you can see that it is again not reducible, because if you draw the K-map, you'll notice that these two minterms are not adjacent and these two minterms are not adjacent, so you cannot take common factors. Okay, so this is the simplest form for the XOR and XNOR gate, and it is always the case for XOR and XNOR gates. No matter how many inputs you have, they will not be reducible. Okay. Now, there are properties of the XOR gates, and we can show them easily. Okay, for example, you can show that XOR is commutative, just like XNOR as well. Okay, so XOR is X XORed with Y is the same as Y XORed with X. Okay, it's commutative. It is also, surprisingly, it is associative. Okay, X XORed with Y, and the whole thing XORed with Z is the same as X XORed with Y XORed with Z in brackets. Okay, or you can remove the brackets altogether, and it's still the same answer. Okay, you can also prove this using these definitions here. Okay, also there are other properties of the XOR operation or gate. Okay, the first property is X XORed with 0 is equal to X. Who can tell me how we can prove this property? Again, okay, we use the definition. So X XORed with Y is X complement Y, ORed with X Y complement, right? Now we have our X is X, and our Y, we have it as 0, okay? So that is equal to X complement, and with what? With 0, all right? ORed with X, and with Y complement means 0 complement, which is
1.
1, excellent. So this cancels and you have x, so which equals the right hand side. I should start with the left hand side equals, and this equals the right hand side. Okay, we proved the first property. Okay, by the same method you can prove the second, third, fourth, and fifth as well. Okay, so now x, but you can also argue that logically. Okay, and you can say, well, I have a 0 at one of the inputs of the XOR gate. So I have an XOR gate here. And I have a 0 here. And I have x, okay? So if you check the truth table of the XOR gate, you'll find that whenever you have a 0, in let's say that this is the most significant variable in the truth table, okay? So you have 0, 0, 1, 1, and then you have x, which is 0, 1, 0, 1. The XOR will be 0, 1, 1, 0, right? This is the XOR. And this is my x, and this is my y, okay? So my y is only these two rows here. Y is set to 0, okay? You can see that. It's a subset of the truth table, okay? So whenever my y is 0, the XOR gate will take the value of x. You can see that here, okay? When x is 0, the output is 0, and when x is 1, the output is 1. So it is, in general, it is going to be x, okay? By the same thing, you can argue, well, what is x XORed with 1, okay? Using the truth table, and then you can arrive to the same conclusion, okay? One of the properties that is really interesting, okay, let's just try to prove it together, okay, is this one here. This one here, okay? This one here means that, so how can I prove it? Let's start with x XORed with y complement and see where does this gets us, okay? So it gets us by definition to x complement ANDed with y complement, ORed with what? X ANDed with y complement complement, okay, which equals x complement y complement ORed with xy, okay, which is what? By definition, if you remember the definition of the XNOR gate, right? Yeah, so this is nothing but x XNORed with y complement, okay? By the same argument, we can derive x complement or x ORed with y, and that equals x complement complement ANDed with y, ORed with x complement ANDed with y complement, okay? And this actually reverts to the same expression, which is x XNORed with y, okay? So this expression winds up being XNOR, and this expression winds up being also XNOR, okay? So it must be that this equals this, and this equals this, and this equals this as well, okay? So graphically speaking, no matter where the bubble is, okay, so if you have a bubble at the output, you can either transfer it to one of the inputs or keep it at the output, okay? All right, so I can move this bubble here like this, or move it here like this, or I can start from here and move it to the output like this, or I can start here and move it to the output like this, okay? So all of these outputs of these gates are equivalent, okay? You got it?
Doctor,
Yes.
does this mean if we had two bubbles, no matter where they are, they cancel each other?
Yes, that is correct. Yes. So if you have a bubble here, okay, another bubble here, then they cancel each other. Yes, because this bubble can be moved here. Okay, then you have a bubble here. Okay, and this bubble moved here, and you have two bubbles here, so they cancel each other. Okay, excellent. So let's take an example in which we want to convert this XOR gate, okay, using these properties here. Okay, actually all of them. Okay, using these properties here, I want to convert this circuit, which is composed of XOR gates. I want to convert it to all XNOR gates. Okay, so how do I do that? First of all, again, we do the same thing as we did in the NAND and NORs, right? So for example, if we put a bubble here, we have to invert it so that we maintain the same functionality of the circuit, right? Are you following?
Yes.
So now this is checked. Okay, we converted this to XNOR. Okay, what about this and this? Okay, now by this property here, by this property equals this, I can move or from here to here, right? I can move this bubble here to the output and this bubble to the output, right? Okay, so I'm going to move it here and move this one here. Okay, now the only thing that is not an XNOR now is this one, so I'm going to convert it to XNOR, but the circuit is complemented now, so the output is going to be Y complement, not Y, right? I want Y using XNOR now. How do I do that? Just add another XNOR. Okay, okay, and if you want, actually let's just make it XOR. Okay, let's make it XOR. All right, and I want to XOR this with 1. Okay, all right. If I XOR this with 1, what do I get at the output? Y complement XORed with 1. What do I get from these properties? Y complement XORed with 1 is X complement. X XORed with 1 is X complement. So I will, if this is X complement and I XORed with 1, I get X, right?
Yes.
So if this is Y complement, I get Y, right?
Y.
But I need what? I need an XNOR, not XOR. So I put a bubble here, okay, and a bubble here as well. Okay, so they cancel each other. But instead of this bubble, at the input, okay, I put a what?
0 instead of 1.
Yeah, change this to, instead of 1, 0. Excellent. Yeah? Any question? Okay, so let's have, let me just erase everything here, okay? Forgot to erase it, okay? Now for this circuit, this is simple. Okay, let's do this one here, okay? We would like to re-implement this circuit using the minimum number of 2 input XOR gates. So we would like to minimize the circuit using the minimum number of 2 XOR gates, okay? All right, you will notice that there are reconverging fan-out branches, and for this reason there will be some cancellations in the terms. Okay, so this fan-out branch here, okay, you can see that there is a fan-out branch here, but it reconverges here, right? So this reconvergence here we'll get rid of some of the variables, okay, and we will have a simpler expression. Remember that if you XOR X with itself, you get a 0, and if you XOR 0 with something, you get the same thing, right? So XORing with 0 means it's the identity of the XOR gate, so you just get rid of it. Okay, so we would like to see what get canceled at the end and what does stay. Okay, so what is the equivalent, the minimum equivalent of this circuit using XOR operations. Okay, so let's start by marking the output of every gate here. So this one here is the output of this one here is A XORed with B. Simple, right? What about the output or the input, other input of this one here? It is coming from B, right? Yeah?
Yeah.
So what is this now at the output? It is basically A XORed with B, and by associativity, I can just XOR that with B, right? And then complement because we have an XNOR here, okay? But these two, as we know, will become a 0, right? So the whole thing becomes what? B XORed with B is 0, and A XORed with 0 is A, right? So the whole thing will become a complement, right?
Yes.
Okay, cool. So I have a complement here at the input, and for the other input, for this XOR gate here, okay, what do I have? I have A XORed with C complement, okay? And then I have a B here, so I have A XORed with C XORed with what? B, and I move the complement to the outside. Okay, do you see that? So originally it was A XORed with C complement and then XORed with B, right? So I just used associativity. First of all, I used the property that says, well, I put a bigger bracket and then move the complement outside, right? Yeah. And then by associativity, this is nothing but everything XOR together, right? So this is nothing but this, right? A XORed with B XORed with C. And then you have a complement. Okay, so the output Z is nothing but what? It is A complement. Z is A complement XORed with what?
C.
A XORed with B XORed with C, right? And then complement. So we know from one of the questions from your colleagues, okay, that these two complements will what?
Cancel.
Cancel. Excellent. So eventually we have A XORed with A, XORed with B, XORed with C. And these two A's will cancel. You have 0 XORed with something. That is the same thing, right? This is B XORed with C. So this is the minimum of this circuit, and this circuit becomes just a single XOR gate with B and C as input and Z as output. Okay? All right. So this is because of the, as I told you, because of the reconverging fan-out branches, okay? But in this circuit here, we don't have any reconverging fan-out branches. So we don't expect any minimization here, okay? That's why we didn't try to minimize this, all right? Any question? Okay, let me move on. This is an old quiz question, okay, of mine. So we are given that this equation, Boolean equation, is true. Okay. We are given that this Boolean equation is true. Okay. This is given, right? So A XORed with B XORed with AC complement. Okay. So there is an AND gate here. Okay. And an inverter here to the C. And this equals to B XORed with C. Okay. I would like to manipulate this expression and imply the value of A ORed with C complement. Okay, this is the requirement here. First of all, the required expression, you can see that the required expression doesn't contain any B. So if there is a way for me to cancel the B from the original equation, that would be great. Anyone can suggest something about this? Remember, the algebraic equation are the same, okay? In algebraic equation, if you have, for example, in both sides, you have +1, for example, and you'd like to get rid of it, what do? You subtract
And
1 from both sides, right? What if you you'd like to get rid of the B from both sides here? What do?
We XOR B on both sides.
Excellent. So we do XOR B to both sides so that the equation remains the same, right? And then we get this equation because the B now cancels, okay? By associativity and commutativity, the B cancels, okay? So we get A XORed with a C complement is equal to C. That's it, okay? You get that? Next. Who can suggest something here? Revert to the definition of the XOR gate, okay? So I have a complement in the left-hand side, a complement ANDed with a C complement. This is by definition, ORed with what? A ANDed with a C complement and then complemented. This is still equal to C by definition, okay? I just rewritten this according to the XOR, the definition of the XOR gate, okay? All right. Now, A complement ANDed with A. What is that? A complement ANDed with A.
0.
0 ANDed with anything is
0.
0. And ORed with something, it is identity for the OR, right? So this whole thing cancels. So I'm left with only A ANDed with this one here. And using the Morgan's law, I can complement what is inside the bracket. So it becomes what? A complement ORed with C, right?
C.
And this equals to C. Using the distributive law, okay, I can distribute A over A complement and C to get what? A complement, which is 0, okay? And then AC, all right, is equal to C. Okay, what can you imply from this equation?
That A is always 1.
Must be. It's not always. It must be 1 because of if the equation, look, this is the logic here. If the equation is valid, then A must be 1, okay? It must be 1, okay? We imply that A is 1 by the AND identities, okay? All right? And if A is 1, okay, then A ORed with C complement must be what?
C complement.
Come on.
Sorry, I mean 1.
Yeah, okay. that I mean, confusion happens, but it's fine. Okay, don't do this mistake in the exam, please. Okay. So A ORed with, I mean, A is 1, so 1 ORed with anything is 1. Okay, so the 1 is the what we call the I think it's called the null identity. Yeah. So anyway, I mean, if you OR 1 with anything, you get 1. You don't get so 1 is the controlling value. Okay, 1 is the controlling value for the OR gate. Okay, next. Any question about this before we move on? Okay, let me move on. So now, a related problem is the odd and even function. They are very closely related to XOR and XNOR gates. Okay, so let's define them first. Okay, define an odd function. An odd function. Okay, so Boolean functions usually are very easy to define because they are either 0 or 1. So we can define it by identifying the ones of the function. Okay, so an odd function equals 1 if and only if the number of ones in the input is odd. Okay, if the number of ones in the input is odd, we get a 1 in the output. Okay, of the odd function. Okay, so now you have an odd number of ones in the input, and you get your output. Okay, which becomes 1 if the input is odd. So the total number of ones of the inputs plus the output is even, right? It's even because odd plus 1 is even. Okay, so odd functions can be used to generate an even parity. That's the reasoning for this sentence here. Okay, so we use odd functions to generate even parity bits. Okay, any confusion or something not understood about this? Is it clear?
Yes.
Okay. All right, so again, odd functions. An odd function equals 1 if and only if the number of ones in the input is odd, and therefore we can use the odd functions to generate even parity bits. Okay. By the same analogy, we can define an even function that equals 1 if and only if the number of ones in its input is even, and therefore even functions can be used to generate odd parity. So it's the other way around. So even parity, we use odd functions to generate them, and odd parity, we use even functions to generate it. Okay. So and also to implement odd functions, we use XOR gate. Okay, odd functions, just relate them with XOR gate. Okay, because why? Because of the if you look at the truth table of the XOR gates. Now, if you have X and Y, 0, 0, 0, 1, 1, 0, 1, 1. Okay, and the XOR of them will be 0, 1, 1, 0. Okay, now it is clear. It is not very clear from two variables that whenever the number of ones in the input is odd here, we have a 1. So it is clear here that 2 input XOR gate is even. Okay, then we can use associativity, okay, to prove that more than 2 input XOR gate is also odd. Okay, is also odd function. So the total number of ones in the input and output is even, but the function itself is odd. Okay, so if you have 3 variables, okay, X, Y, and Z, and then you have the XOR, Okay, then let me just 0101 01 01. Okay, and then 0011 and 0011. Okay, and then 4 zeros followed by 4 ones. Okay, all right. Now, what you can do in order to calculate the XOR is to use associativity now. Okay, you calculate the XOR of these two. Okay, and then you XOR the result with Z. Okay, so the XOR of these two is 0, and 0 XORed with 0 is 0. You get that? Now this is 1, because 0 XORed with 1, 0 XORed with 1, 0 XORed with 0 is 0, and XORed with 1 is 1. Okay, next it is 1 again. Okay, you can see that just by looking at the number of ones in the input, you can calculate the output of the XOR gate. Okay, if the ones are odd, then you get a 1 in the output. If the ones are even, then you get a 0 at the output. Okay, so here you can see that the number of ones is even. Let's see whether we get a 0 or a 1 here. We expect a 0 here because the XOR is odd function. So 0 XORed with 1 is 1, and 1 XORed with 1 is 0. Okay, all right. By the same logic, 1 XORed with 0 is 1, XORed with 0 is 1. Okay, okay, here we have 2 ones, so we expect the result to be 0. So 1 XORed with 0 is 1, XORed with 1 is 0. Okay, and again here 2 ones, so we expect a 0 at the output. So by definition, it's here it's 3 ones, so we expect a 1. Okay, so 1 XORed with 1 is 0, XORed with 1 is 1. Okay, so this is why XOR is odd, and if you add another variable, then you just use the associativity again. Okay, and then you get, so again, if you want to calculate it very quickly, you just calculate the number of ones in the input. Here, for example, here it is 1 1. Okay, and therefore the output must be 1. Okay, here it is even number of ones, so the output must be 0, and so on and so forth. Okay, you get that? Okay, so by this illustration, we know that to implement odd functions, we need an XOR gate, and to implement even function, we need XNOR gates. Okay. Okay, so let's take an example. Okay, we would like to show. Let me just erase the. We would like to show an even parity code generator. Okay, so we would like to generate the whole code, the whole parity code. Okay, for a BCD 8421. Okay, code. Okay, so we have an input of a BCD 8421 code. Okay, and we would like to generate an even parity code. Okay, for that. So my input is how many bits?
4.
4-bit. And we can name them something like, for example, like last time, Y3, comma, Y2, comma, Y1, comma, Y0. And I know that this is my, let's just suppose that this is my most significant bit and this is my least significant bit. Okay. And for the output now, notice that I'm generating the code now, not just the parity bit. So what is the size of my code, my output?
1.
Again, I'm not just generating the bit, the parity bit. I'm generating the whole code.
1 plus 4.
Which is 5, basically. The output is 5-bit. Okay, and it is basically composed of P, which is the parity, plus the code itself, the input code itself, which is this one. Okay. All right. So this is my output. Okay. Now to generate P, I need what? Now I need an even parity generator. So I know that I need what? Odd function, right? If you need even parity, you use odd function. If you need the odd parity, you use even function. Okay. Always reverse that. Okay. So for the parity bit, I need to use odd function. Okay. And for these bits here, I just need wires, more wires to route them. I don't actually, I don't need to show them, okay, because they are part of the circuit. So this is the circuit now. Using the associativity of the XOR gate, I know that this is my circuit, because the whole thing here, my P is nothing but Y0 XORed with Y1, XORed with Y2, XORed with Y3. This is an odd function. An odd function uses XOR gate, okay? All right. So the code generator output, as I mentioned, is the whole thing here, which is this is the code. Okay. It's the parity bit plus input BCD code. Okay. All right. So you have a sender, you have a circuit that generates the code. Sender, in which you have some code generator here. And then this code generator is going to be sent over some channel, okay, to a receiver. Okay, and the receiver needs to check whether the code is valid or not, right? So I have a parity checker here. Okay, the parity checker, the purpose of the parity checker is to generate an error signal. If the error is 1, it means that my parity is wrong. If the error is 0, it means that probably the parity is correct. Okay, let's see how we can do now the rest of the story, which is the parity checker. Okay, so the parity checker, okay, notice that we are receiving we know that we have generated an even parity code, okay, and therefore we can generate what we call an error signal E, such that E is equal to 1. E is equal to 1 if the code contains an odd number of ones. Okay, because why? Because we are expecting an even parity. Okay, if you receive an odd number of ones, then your error must be 1. Okay, must be, there is an error in your signal, and therefore look at this. So E is 1 if and only if the code contains an odd number of ones. What is this? It is an odd function, right? It is nothing but an odd function, and odd function we use XOR again. Okay, so the parity checker, the even parity checker, is nothing but this. Okay, we take the code, okay, XOR the bits of the code together, and then XOR them with the parity bit. If the error is 1, then you get an error. If the error is 0, then probably your code is correct. Why did I say probably? Who can tell me why am I saying probably here? I'm not sure if the code contains error or not.
Because it may have 2 errors, and thus it will flip back to 1 to 0.
Excellent. Yeah. So it's still an even parity. Okay. So if you have an even number of errors, they will not be detected. Okay. But odd number of errors will always be detected. Okay, by parity checker. But we don't know how many errors do we have. Okay. The only thing is that the parity is different. Parity means odd or even. Okay. Okay. So in summary, to summarize what I just said, for even parity. So if you are confused or something, this is the two lines that you need to pay attention to. This is the summary of the whole thing about parity generation and checking. Okay, so for even parity generation and checking, use odd function or XOR. Okay, and for odd parity generation and checking, use even function or XNOR. Okay, all right. Now here are some important aspects that you need to pay attention to. We never use more than 2 inputs for XOR or XNOR gate because it costs a lot to have a 3-input XOR. So we use associativity to implement, for example, for this circuit here, for this 4-input XNOR gate. Okay, how do we implement it? Using basically 2-input gates. Okay, so this is fine algebraically, but if you want to implement it in circuits, you use only 2 inputs. So you use associativity in order to split your expression such that it becomes always 2-input maximum. Okay, so this one here is wrong. Okay, whereas this one here is the equivalent correct circuit. Okay, notice that we only have one bubble here because of the properties of the XOR. Okay, XOR and XNOR. All right. Okay, so let me ask you a question. If the question says here, we would like to show an odd parity code generation circuit for the same thing. What is the thing that changed here? What is the thing that changes here? This one here is an even parity. So if we want an odd parity, what do I do?
Just add a circle.
Yeah, just a bubble here. Just a bubble, because again, if you add a bubble here, it means you are XNORing the inputs. Okay, you are XNORing the inputs. Okay. Also, if you are implementing an odd parity checker, okay, then all you have to do is to add a bubble here. Okay, you see the powerful the power of this technique here, parity generation, the power of XOR and XNOR gates. Okay, they're so flexible.